when looking strictly at sig figs is underlining them. So 1 is a sig fig, 2 is a sig fig. The next big deal is I do have a decimal point, so that's going to change the rule set I look at. Because I have a decimal point, to make a 0 significant, I just have to look to the left to see if I have a significant digit. Okay, so I will start with the 0 furthest to the left, and I will look to the left. Is 1 a significant digit? Yes. Which makes that 0 significant. Okay. I move to the next 0. I look to the left. Is 2 a significant digit? Whoops. Yes, so that one's significant. I move to the next 0 and I look to the left. Is that a significant digit? Yes, I just identified that as a significant digit. This is why it helps to go left to right. Because if you start right to left, well, you're like, I don't know if that 0 is significant or not. Does that make sense? Does that work? So when you go through and do this, everything is significant. 6 sig figs. Okay? I'm going to cheat real quickly. Let's see, did I do that right? Looks like I did that right. So the answers your calculator spits out should be 129.04 meters. The next one. What does your calculator spit out for question 4?
4538.77015. Sorry.
That's quite all right. Meters cubed. The next one looks like I screwed up the unit. 0.0. What does your calculator spit out for 5, actually? Anybody do it? 0.0252. Okay. Liters. And then the last one. Calculator also probably spits out something ugly.
0.04544111186.
6 per centimeter cubed. Okay, so question number 3. These are all things your calculator spits out. Notice one of the things that your calculator didn't spit out was the unit. Okay, you have to keep track of that unit and make sure that measurement is included in this. Okay, that answer is wrong. No, it's not, because your calculator didn't spit that out when you did the math. Dang it! What did it spit out when you did that math? So it'll be 129.041. Is that it? Oh, well, that was a bit silly. Okay. So your calculator spits that out, and it ends up being wrong. When you do addition, subtraction, where do you report your sig figs to? The least precise place. So that means we go back and look at our numbers. The first number reports out to the thousandth with TH. Yeah, okay. The next one reports out to the hundredths. The last one reports out to the thousandths. Okay, which means our answer is going to be limited by the hundredths, which means that's as far out as we can report. We can only report to the hundredths. Your answer, we'll just scribble that out, becomes 129.04. That hundredths place only had 3 sig figs. Don't I have a lot more than 3 sig figs? Yes. Was that allowed? Yes. In addition, subtraction, we aren't counting the number of sig figs. And in fact, very often when we add numbers together, the number of sig figs actually increases. Okay? That is okay. That will typically happen. Okay? When you move to the next one, number 4, okay, you're looking at multiplication. Your calculator spits out a whole bunch of different numbers. Okay? How do we figure out where we report? Because this is multiplication, we go with the fewest number of sig figs. The first number has 5, 3, 6. So 3 is our answer. I can only report to 3 sig figs. 1, 2, 3. Okay? We'll even throw in the rounding for this part. The first insignificant number is larger than 4, so I need to add 1, and my answer becomes 45440 meters cubed. Is that 0 significant? No. Okay. If I draw a decimal point, now the 0 becomes significant, and now my answer is wrong. Okay. So leave the decimal point off, and it's now perfectly correct. Notice one of the things that's weird, our meters cubed, we didn't do anything to the meters, it just continues to multiply through. So meters times meters is meters squared times meters, meters cubed. Okay, we leave the alphabet alone, we just simplify it. Kind of make sense? So our answer is 454.0 meters cubed. We'll look at that one, or an example like that one a little bit later. Number 3, 5. 5 would be the next question, not 3, for those of you counting. Okay. It's addition, subtraction, least precise place. I can only report to the hundredths, which means when I go through to look at my answer, I can only report to the hundredths location, which means my answer becomes 0.03. Why'd you get 3? Doesn't it say 2? The first insignificant digit is larger than 4, so I have to add 1 to it, and I get 0.03. I see you. Give me a second. And we throw in our unit of liters because that didn't change. What happened to the amount of sig figs?
Decreased.
It decreased significantly. We went from something where I had 4 sig figs and a lot more than 4. So we had lots and lots and lots of sig figs. I do this one calculation and I lose virtually every single bit of information. Okay? Notice the number that I've got there is effectively a guess. I did legitimate measurements and I end with an answer that is really just a guess. That's a really crappy calculation. So when we tend to do things where we're subtracting numbers, we try to make sure that the difference between those two numbers is as large as humanly possible. Because if they're large, when I lose sig figs, I don't end with a guess. Okay? Does that kind of make sense? Yeah, Ness.
So going back to number 4, the answer, could you just do it as 454 meters cubed with a mistake of 0? Would that be still correct?
Okay, this is your paycheck now, so let's switch out the units.
Okay, I get it.
Do we really want to just delete that 0? Yeah. That makes a pretty big deal. That 0 acting as a placeholder tells us that first 4 goes in the thousands, not in the hundreds. Okay? So the 0 still holds meaning, it just doesn't hold meaning as a significant digit. Okay? And yeah, that is a very common question. We have to be careful with that. Okay? The last one, number 6, we're doing division, so it's based off of the number of sig figs. 3 sig figs and more than 3. So our answer needs to be reported to 3 sig figs, 1, 2, 3. The 4 is less than. It's not greater than 4, so let's say that. Which means I don't have to do anything, I just have to erase those last digits. And I end up with 0.0454 grams / centimeters cubed. Notice nothing happened to the alphabet stuff, but there's nothing to cancel those. Okay, so I have to report those through to the very end. Okay, when we start getting into conversions, which isn't going to be that far out, okay, this notation of a slash is a horrible notation. Everybody wants to do it. Okay, why does everybody want to write out this notation of a slash? What does it mean?
Show separation.
That slash is a division. Okay? If we're going to divide things, really what are we looking at? Everybody's favorite. It begins with F. And be careful. A fraction. So what we're actually saying is I have 0.0454 grams over centimeters cubed. What's the number in front of centimeters cubed? 1. Because if it's anything other than 1, is it 454 anymore? No. So it has to be a 1 there. Okay, why did I place the 454 on top?
It's bigger.
Because when I look at my unit, the unit shows grams / centimeters cubed. This is grams being in the numerator on top / centimeters cubed being in the denominator. How do I know the 454 goes with the grams and not the centimeters cubed?
On the same side as the grams.
It's on the same side as the grams. Okay, there's our slash that delineates the difference there. That number is tied to the one closest to it. It's tied to the grams. That's why the number shows up on top. Kind of, sort of? Okay, so why write out slash and not the stuff in red?
Too much work.
The stuff in red is too much work. So everybody likes to cheat and show this. Okay? It is awesome and fantastic to cheat and use shortcuts when you understand what's going on. There's a reason you're in this class, and it's not because you understand what's going on. Okay? You don't know what's going on, you should use the longhand format. This longhand format will simplify calculations in the long run if you show all that work. If you decide to not show that work, you're going to make your life miserable and hellish when we move into unit systems that you don't understand. Okay, so you should write it out in this longhand format. The last thing I'll address real quickly here is the importance of Sig Figs. Okay? If you want to continue through science, be an engineer, Sig Figs are pretty darn important. Okay? If this is the only class you need, then you probably don't care. Okay? When it comes to Sig Figs in calculations, it is very rare for any instructor to ask a question on Sig Figs and another concept. Okay? The reason being is that that's now two conceptual things that we have to calculate and grade. We can do that in a show your work type place, but if it's multiple choice, I'm now wasting answer choices on a Sig Fig question when I'm testing for something else. Kind of makes sense? So when you see Sig Figs, it'll very much be in something similar, a similar fashion to this. You're given a calculation, run the calculation, tell me what the Sig Figs are. Okay? In this case, we're directly testing you on Sig Figs because we're making the assumption, however valid or invalid, because we can make mistakes, that you can do addition and subtraction. Okay? We're making that assumption. But when we move further on into the semester, we'll be looking at calculations where it's harder to decide what that actual calculation is, which means it's less likely for you to get it right. Okay? So in that case, I want to test on the calculation, not on the Sig Figs. So when you look at the practice exam for exam 2, scan through it. Look for questions that are asking about Sig Figs. Try and identify them. Okay? They should stand out as a glaringly obvious question, and one in such a situation where you actually don't need to perform the calculation. All you have to do is look at your answer choices. Okay, we'll leave it at that. If you got questions about it, because I'm not creative enough to come up with one on the fly, we'll look at it later in the semester. I would argue it's nice to have it all on one slide, so if there's one slide you decide to print out so that you can then memorize, this has all of your Sig Fig rules. Addition, subtraction, moving Sig Figs, rounding, it's all there. So you can print that one slide and always reference that when you run your calculations. Okay? I tried to shuffle the order in here to match the play posit sequence better, and I think I've screwed it up pretty thoroughly. So if you've printed out the slides, I apologize. This is now slide, I think, 67, 68. Okay? So it's a big leap, but we had a question before class started that's addressing this. Okay? So if we looked at a chemical reaction, okay? So this is going to be a good review because this gets at our nomenclature. Solid sodium hydride. Okay? We want to convert that into a chemical format. That's too much text. I don't want to read it. I just want to look at it. Okay? What information do you see there that you could encode? Sodium. What do you know sodium? Na. Good. Continue. I see acid, but I'm going to balk at the acid. Why might I balk at doing anything with the acid yet? There's an awful lot of stuff that happens before I get to that acid word, so I don't want to deal with the acid word yet. Okay? And it could just be a case that you don't know the rest of it. That's okay.
Hydrogen?
Hydrogen? Where does it say hydrogen?
Oh, wait. Oh, wait, no, mine. Which one? Hydrogen? No, isn't that?
Okay. You see You see hydro and you're like, oh, hydrogen. Does it say hydrogen? No, it says hydride. What does that mean? Okay. What that means is I have sodium bonded to hydrogen. And in that compound, as soon as I make that a compound, because hydrogen is the more electronegative element, its ending changes, its suffix changes to the IDE ending. Okay. It's the nonmetal in that ionic bond. Because of that, I change the ending from hydrogen to hydride. So you were right to call out hydrogen, it just didn't say it explicitly. Okay. What else could we add to this? It says solid. Where do I specify the phase? Parentheses at the end. Depending on how your instructor decides to format it, okay, it may show up as a subscript. It may show up not subscript, but ultimately parentheses in the phase. Okay. S for solid. Okay. Then what? Not quite. An arrow does not mean reacts. Plus means it reacts. Okay. Plus what? Okay, now we're moving into the next piece, acetic acid. That is our next whole piece. Now you can flavor. I have no idea what I was going to try and say. Acid. Okay. What does the acid mean? Okay. So we know the phase is AQ. Good.
And then you add the hydrogen in the front.
And we know we have hydrogen in front.
Or was it always in the back?
No. So now the rest of it. How do you figure out the rest of that? Well, the acid just tells you H and AQ. The rest of it must be the acetic part. Okay? So what is that acetic part? Okay? Going back to nomenclature, our rules for naming acids, we will change the suffix to an ic acid, and we do that for our complex acids or our ternary acids. The ic corresponds to what former suffix? Ate. So really what we're looking at here is acetate. Okay. When I make acetate with hydrogen and make it aqueous, it now becomes acetic acid. Okay. So what is acetate then?
C2H3O2.
Acetate is C2H3O2. How do you know that? You have to memorize it. Okay? And I usually get people balking at this. What is Fe? Iron. How'd you know that? You memorize that. Don't start complaining about acetic acetate names. You already memorized a bunch of stuff. I'm just telling you more stuff to memorize. Okay? Your complex ions are now effectively a new element. You have to memorize them. Okay? There are tons of complex ions. If you go back to that nomenclature video, there's 7 that I tell you to memorize. Memorize those 7. Okay, you want to memorize more? By all means, you're free to. Go ahead. Okay, you may be expected to memorize more for the lab.
Do we need that negative charge?
We don't need to be worried about I lied. We'll come back to that charge. Okay, there's a reason we don't have to worry about it quite yet, but we should be worried about it. Okay, to produce. To produce is our reaction arrow now. To produce what? Aqueous sodium acetate. What can we start to write about that one? Sodium is Na. I heard someone throw in the aqueous. I really appreciate when you guys tell me the thing at the end of the thing.
Acetate, C2, H2.
AQ. I mean, that's fair. It starts with it. Okay. And then the middle part,
Acetate.
I know it's acetate. Because I just did acetic, I know that the formula for acetate is C2H3O2. Okay. And plus sign. I really wish I color-coded this better, and I apologize. I'm all over the map. And hydrogen gas. Okay. We're just going to write H for the moment, and then gas. I heard a couple people say H2. Why'd you say H2? Because it's diatomic. Okay. We'll let that hang for the moment. Okay. It is diatomic. We have to write it as H2. Okay. We have to know that extra information. Okay. Before we get into that, there was a question about the charges. Do I need to be worried about charges? Every time you draw a formula, you have to make sure you provided the correct formula. The charges must balance. So let's go all the way back to the very beginning, because I should have talked about it first, so we can rewind back. If I was funny enough, I would try and do that, but I can't.
It's down.
Yeah. What is the charge on sodium? Sodium is a +1. What is the charge on hydrogen? Okay. I heard a +1 and I heard a -1. Why are you saying +1? Okay. Because in that first column, we would assume it would be a +1. Does anybody see a potential problem with it being +1? Yeah, it would be impossible to balance the charges. Okay. What is the charge on that hydrogen? It's actually a -1. Okay. How do we know that? It comes to the balance of electronegativities. Okay. And if we look at our electronegativities, hydrogen is more electronegative than our sodium, which means what is it going to do when I bring neutral sodium and hydrogen near each other? The hydrogen is going to steal the electron. If it steals the electron, it becomes negative. So why do we make you memorize all those charges? It's a good question. It's a really good question. One I don't have a very good answer for this particular example. Okay. When we move to the next one, okay, because this is a fun one. Acetate has a -1 charge, and you knew that because? You memorized it. Good. What's the charge on the hydrogen? Why did you just switch it to +1? Shouldn't it be -1?
Balance out.
Okay. We need it to balance out. Anybody see a reason why hydrogen might be tricky? Yeah, hydrogen can be both +1 and -1 depending on the conditions it's in. Those conditions being the electronegativity of the elements it's bonded to. Okay. Remember, if you go to the tutoring center, your periodic table there has the first row, hydrogen and helium, offset. Why is it offset? Because hydrogen and helium don't follow the trends very well of everything underneath. They kind of go both places. It is very often the case that you will see helium above beryllium. Why? What is the electron configuration for helium? (1s2). What is the electron configuration for beryllium? Outermost. 2s2. Helium fits nicely above beryllium. They have the same kind of ending. That would be placing it in the s block. Okay. However, if we think about helium's reactivity, does it react the same as everything in that column? No. What does it act as? A noble gas. So where do we place helium? Above the noble gases, because it better matches the group or family. What happens with hydrogen? Hydrogen typically carries a +1, but there are cases where it can be -1. Where's the -1 family? Our halogens. You mean the column immediately before helium? Yeah. You can sometimes see hydrogen and helium placed next to each other at the far right of the periodic table, because it helps, again, predict their chemistry. Okay? Their chemistry becomes a little bit bizarre because they only have access to that first energy level, which means they can be noble, if you will, by either gaining, or for hydrogen, it can either gain one to look like helium, or it can lose one to look like,
Entirely different.
what if it loses one? How many electrons would it have? 0. It effectively places it as a noble gas. It's perfectly symmetric with nothing in it. Okay, as a 0 noble gas. Those are being like, what? That's bizarre. Okay, don't worry about it. Hydrogen, +1 and -1. Okay, depends on the state that it's dealing with. Okay, move over to the product side. Sodium is a +1, acetate is a -1. How do we know sodium's a +1?
You said it before.
This one is one that we memorized. That first column is +1. As long as we kind of ignore hydrogen, the metals hold true. Acetate we memorized. H2 at the very end. Trick question, there is no charge.
They cancel each other out.
Okay? It's not even that it cancels each other out. Okay? Charges. We talked about charges. There was a very important word that came before charge. Ionic. Is there a metal or a non-metal in H2? Or sorry, a metal in there? No. Which means it's not an ionic compound. We don't look at ionic charges. Okay? So we do have to consider charges when we go through and predict our formulas. In this case, I was really nice because everything balanced outright. That's not always the case. Yes?
So does diatomic mean that it could be -1 or +1?
Diatomic means it's 0.
Oh.
Yep. And that's its oxidation state, which again we haven't covered yet, but I think that's next weekend's video. Maybe even the one after that. Okay? So, getting back to that H2, how do I know it should be written as H2? Okay, this again comes to a memory thing. There are certain elements that are diatomic. We have to have those memorized. Okay? There are 7 of them on the periodic table. Hydrogen, nitrogen, oxygen, or fluorine, chlorine, bromine, iodine. Okay, so we'll go through a couple little devices to help you remember that. If we go through and circle them, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. What does that look like to you? Kind of looks like a 7, right?
I was going to say Tetris.
Kind of looks like a 7. Okay, well, how many things did I circle?
7.
6, right? 1, 2, 3, 4, 5, 6. But it's 7. Oh, I forgot one, hydrogen. There you go. Sort of tells you that you have to memorize 7. Sort of. Those are being like, couldn't I have circled like anything to make it 7? Yeah, I know. It's not perfect. Okay. The other one. Okay. I'm telling you all like my least favorite ones, by the way, first. Okay. A colleague used to play a lot of hockey. What does this kind of look like? A hockey stick and a puck. Okay. So any way you remember that can help. The way that, for whatever reason, probably because I was so immature when I learned it back in high school, was this little phrase: have no fear of ice cold beer. Have begins with H, which also happens to be hydrogen. No. Nitrogen, fear. Fluorine, of. Oxygen, ice. Iodine, cold. Chlorine, beer. Bromine. Okay. It ain't perfect, but it works. Okay? Ultimately, you need to know them. So anytime you see something referenced as hydrogen or bromine, you know it's diatomic. It has to be specified as that too. Kind of make sense?
That's when it shows up by itself.
That's when it shows up entirely by itself. Okay? What if I wanted to look at a single hydrogen instead of the diatomic species? Which is a harder question. And I don't want to erase everything. So there's that versus this. And to be extra tricky, we can even throw it in as a gas. Call it blue box and red box. Name the red box. Or the blue box, I don't care. Okay, which one are you naming? Either, unfortunately, doesn't work. What is the difference between the red box and the blue box? There's two of them. Okay, when I have two of something, right? Two elements, what do I have?
Die.
Ion.
I have a molecule. I have a compound. Okay, when I only have one, what do I have? We have to be careful. An atom. The blue one I would reference as a hydrogen atom. Okay? And not hydrogen ion. It's not charged. This is a hydrogen atom. Okay? What if I just say hydrogen? Unfortunately, we can just say hydrogen, and it goes to the default state of hydrogen. What is the default state of hydrogen? Diatomic. So if I just say hydrogen gas, I'm referring to H2. Okay? If I say hydrogen atom in the gas state, I know it's a single hydrogen. Right? So if I asked for a bromine atom, you would write Br. If I just asked for bromine, you would write Br2. Okay? Yes, it's tricky. We just kind of got to deal with it. Questions? Okay. So I know I made you watch a whole bunch of videos on not this topic right now, but we're shifting gears. I apologize. Okay. Mathematics simplifications. If I had you write that out, how many of if I said write out 4 times 4 times 4 times 4 times 4 times 4 would do it? Okay, most of you wouldn't do that, right? You're like, no, it's dumb. I don't want to do that. What did you suggest?
4 to the 6th power.
4 to the 6th power. Okay. Why are you doing that?
Because you're lazy.
You're lazy. You've come up with a shorthand to do that. Okay? It's a repeated calculation. Because everybody wants to come up with a shorthand, that's why we invented exponents. Okay? So 4 to the 6th. It does the same thing. It scales that out for us. So we will see exponents pop up. Typically where the exponents pop up is looking at powers of 10, which we'll look at here in a second. Okay? So it's all about laziness. There are some exponents that are more common than others. For instance, squared. That's to the 2nd power. Okay, why? What happens if I look at a square? How would I measure its area? Length times width. Okay, and if those were centimeters, this would be the length centimeters times the width centimeters, and I would get, for lack of a better description, LW centimeters squared. Why cubed? Because when we look at a cube, we now have a 3-dimensional object. We added a new dimension, length, width, height, and we get centimeters cubed. So you will hear reference to squared and cubed fairly frequently, typically in response to units. Okay? The other exponents we use are all based off of our powers of 10. Okay? Our powers of 10. Powers of 10 are nice because it can take a number that is really, 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 really big and it can simplify that number down. Okay? So if I look at that number, that top one there, how many sig figs? There is only one. There's no decimal point, so those zeros are placeholders. Okay? So if I want to write that number out without including all the zeros as placeholders, I can say this is 1 times 10 to some power. That some power is how many times I shifted the decimal place. So where's the implied decimal point in that first number?
The last zero.
The very end right here. So if you take a look at your calculators, what you will probably see outlined on many of them is this. What did we just count? How many times we shifted the decimal place. Right? Which I didn't do a very good job counting, but I think it was 6. I always draw it and then not count it. So we could call this 1 times, oh, it's written right there. Look at that. 1 times 10 to the 6. Look, see? If you solve it, you get the answer. That's amazing. Okay? We can also do the same thing with numbers that are really, 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 really small. Why would we do that?
For the exact same reason in reverse.
Okay? There's 2 reasons. One we'll look at here in a second. Admittedly, the slides probably have it goofed. Okay? But The secondary reason has to do with the capacity of the human brain. Your brain is tiny and it sucks. Okay? Let's rephrase that before you think I'm insulting you. Our brains are tiny and they suck. Okay? They can't deal with really large numbers. They can't deal with really small numbers. If I take this first number that's really, really big and I now write it as 1 times 10 to the 6, I go, oh my God, 10 to the 6, that's something big. And oh, 1, I can deal with that. I can breathe. Okay? And it may seem simple and stupid, but that's exactly why we're doing it. Okay? We're trying to convert this number that is massive into a system that our human brains can wrap around. Okay? So that is one reason behind it. The other reason has to do with Sig Figs. Okay? So if I took a look at that first measurement, right, you might ignore all the words because I'm pretty sure I screwed those up. Okay? If I take a look at that first measurement up there, someone went through and measured the distance or approximated the distance from the Earth and the Moon. Okay? They measured it, okay, by using a 1,000-foot stick. They just took the 1,000 and went, there's 1, 2, 3,
And then when they were done,
and they
still
counted
had
it out.
2 meters
Okay?
after they were done.
And so, touche, a 1,000-meter stick, and they came up with this number. Okay? How many of those zeros are significant?
1.
No. These are significant. Right, so, well, why are those significant now? According to all the rules that you gave me, Mike, those aren't significant. I added some context to this. I said they took
They used 1,000.
a 1,000-meter stick and used that to measure. The very first measurement I make is 1,000. As I continue to add, I notice that after 10 of them, what happens? It becomes a 0. That 0 is a measured value. Okay? But the number as written doesn't help me identify that those zeros are significant. Okay? I now lose information because the measuring device happened to randomly fall on an even 100. So those 2 zeros appear to be insignificant. How could I rewrite this number to make sure that everybody knows that those zeros are actually not 1 through 9?
Use scientific notation to include a decimal point.
I could use scientific notation by including a decimal point. Okay? So I'm going to break that into 2 things. I could include a decimal point. Whoops. Decimal point. Why is that wrong?
Because those 3 are significant.
Now those last 3 have all of a sudden become significant. I didn't use a 1-meter stick. I used a 1,000-meter stick. Okay, so those zeros aren't significant. So I can't just put a decimal point there. So I'll put the decimal point here then. This gets back to Ness's question where we referenced paychecks. Your paycheck, you're probably happy either way, but your first paycheck is either 406 million or it is 406,000. That a little bit different? Yeah. Okay? It doesn't always work. Okay? So how do I rewrite this? This is where scientific notation comes in. Okay? One option is we can go through and say 406,300 decimal point times 10. And what I'm implying now is that I need to shift that decimal point, right? I'm saying it's right there. I want it to go up how much further? 1, 2, 3 places. So I could call this times 10 to the 3rd. Should it be positive or negative? Is my number big or small? Big, it's positive. Okay? That works. That maintains the meaning. Is that scientific notation? No. Why not? Because scientific notation has arbitrary rules associated with it that we have to follow if we're in scientific notation. What are those rules? Okay, kind of elucidated at the bottom of this. To be scientific notation, my first significant digit must show up in the ones place. So I get 4 decimal point 06300. I'm now listing all of my significant digits. Now I'll do times my power of 10. Okay? So we go back to our original number. There's our implied decimal point. How far did we shift? 1, 2, 3, 4, 5, 6, 7, 8 locations. Is my number big or small? Big, so it's a positive 8. Those of you that weren't learned this will, if you move to the left, it's positive, or right, negative. You don't have to go very far with different practice questions to realize left and right is a bad option, because depending on which way you're converting it, you're going to be changing it backwards and forwards. So evaluate your number. Decide, is it big? Okay, it's positive. If it's small, it's negative. Okay?
Do you have to add the plus?
You don't have to specify the positive. I only specify it as an extra emphasis, but that's it. Okay, there were a couple hands first, so.
Couldn't you just convert it to kilometers?
Different question. We'll get to that.
When you say small number, can you specify?
Okay, let's clear all that. Is everybody okay with that? What was there? Because I can go back. I have learned that one. That's a nice undo. Okay, so as long as everybody's okay, we've got two numbers here. Which of those numbers is small? Why is the second one small? It's less than 1. Okay, it's looking at where we shift. So when we're talking about small and large, we're referring to the absolute value, so I ignore positives and negatives on the numbers. Okay. Typically, because we're looking at measurements, we should be looking at positive values, because I can't have a negative measurement. Okay. I can have a negative chain. Yeah. So this bottom number is small. So if I converted that to scientific notation, first number in the ones place would be 1 decimal point 16 times 10. 1, 2, 3, 4, 5, 6, 7. 7 places. Is my number small or big? Small, that's minus. Does that work? If it's less than 1, you're now just changing the sign to being negative. You're still applying the same rules, okay, on how far it shifts. You're right, you're dealing with small and large. That's why I said absolute. We'll ignore positives and minuses out front. Okay. It's proximity to 0. If it's really close to 0, make it a negative power of 10. If it's far from 0, make it a positive. Here. Okay, I saw another hand pop up. No? Okay. So that's our scientific notation. Did I lose connection? Come on. There it goes. In our metrics, what's going on? Our metric system, we talked about, okay, our basic units, meter, gram, liter, and seconds. Okay, remember, I specified these as core units. Okay? Basic tends to mean base, which everybody says bottom. So these are core units. Officially, this table is wrong out of your textbook. The basic unit for mass is not grams, it's kilograms. Okay, so officially, that is wrong. Implementation-wise, it's good. Okay, I just want to be on the record for that. Okay, these are arbitrary human inventions, so you can't go through and say, well, but an inch is an inch. No, an inch is because somebody said this is what an inch is. Okay, these are entirely human inventions. Somebody didn't come down and say, no, this is what it is. Okay, in one of those deep booming voices. Okay, so how could we measure really big and small? Well, we had our powers of 10. Okay, we could convert things into scientific notation. But a suggestion was made, couldn't we have changed the unit system? Okay? So if I was going to, say, measure the distance from the front of the room to the back of the room, meters, okay, or if we can even pull it American, what unit system would you use to measure that? Feet. If I want to measure from the front of this room to LA, why aren't you using feet?
It's a bigger distance.
Okay, it's a bigger distance. We shift the unit system to deal with those larger scales. Why would we shift the unit system? Because if we measured it in feet, our human brains wouldn't be able to comprehend what that meant. So we invented a new unit system to help us understand it better. Hence, we invented miles.
Yeah. You get to human, then you're like, I lost count.
Yeah. I lost count well before Yuma. All right, so how do we do this in the SI system? All right, in the American system, we went from inches to feet to yards to miles. Okay? Inches to feet was 12. Feet to yards, 3. Let's not do yards because I don't know that one. Let's go feet to miles. 5,280, which I heard some internet meme about tomatoes that I was like, what? But it actually kind of made sense. I just forgot it. So you can look it up. Okay? That system makes utterly no sense. You've got 12, you've got sets of 12, you've got sets of 3, you've got sets of 5,280. Seriously? Okay? This is where the metric system comes in. The metric system goes through and now does powers of 10. Okay? So for each of those large shifts, we invent a multiplier that we could put in front of our core unit. So if I have a really small measurement, meters doesn't make a lot of sense because that's a really big thing. So instead I'll measure by centimeters. Okay, well, what is centimeters? It's a smaller measurement unit. Okay, how much smaller? 100 times smaller. Okay, power of 10 to the negative 2. 10 to the negative 2, you will notice, is not 100. What is 10 to the negative 2? 1/100th. 1 divided by 100. Okay? So these powers of 10 include information about where you should be specifying your calculation. Okay? That's a lot of prefixes to have to memorize. So don't. You've got 3. Is that 3? That is 3. That you absolutely need to memorize. Kilo, centi, and milli. Okay? Again, your lab may ask you to memorize more. Okay? But those 3 you absolutely need to know. Kilo, we use a lowercase k. It is lowercase for those of you in the Tuesday lab. Okay? And that means 10 to the third. 10 to the third power. Okay? Not 1,000. It means 10 to the third. Centi, we use C, and that means 10 to the minus 2. Not 100. Not 1 over 100. It means 10 to the minus 2. Milli means 10 to the minus 3. Okay? You do not have to do it this way, but I will tell you this way consistently works. Virtually every other way I've seen in the tutoring center, and even how I was trained, brings it down to a 50-50 chance of placing the numbers in the wrong place. Okay? The method I'm about to show you always works. It's amazing. Okay? I wish I had known about it. Okay? So, let's take a look at some numbers here. I have 1,200 meters. So what I'm going to do is convert that to scientific notation. So that would become 1.2 times 10 to the third, because I did 1, 2, 3 shifts. Was this a positive third or a negative third? Positive third, because 1,200 is big. Okay? I need to include my unit, meters. Okay? My number and new unit, all I have to do is lop this section off and interpret it as far as the alphabet goes. So I end up with 1.2. What did 10 to the third? What was our symbol for 10 to the third? Kilo, which means K. Did I do anything to the core unit? Nope, it stays there. My new number in unit becomes 1.2 kilometers. Simple. Do the next 3. For that second one, we shifted the decimal place 2 places. So this would be times 10 to the second. Is our original number small or large? Small. That needs to be negative 2. Okay. The next one you'll notice is the same shift, so I'm just going to write that one. And then the last one, 1, 2, 3 places. 10 to the third. Why are you saying negative?
It's small.
Our number is small. Okay? What did 10 to the minus 2 mean? Centi. Centi. 10 to the minus 3? Milli. So we get 1.2 centiseconds, 1.2 centiliters, 1.2 milligrams. Everybody seems to freak out at centiseconds just because it sounds weird. Doesn't matter, it's right. Okay? That's what we're doing with our powers of 10 and those prefixes. Those prefixes hold meaning. If you don't know the meaning, then you can't do the conversions later on. Okay? So, some other things that are going to pop up here. English, there are 1,000 meters in 1 kilometer. If we wrote that as mathematics, what would that be? 1 kilometer. Ah, that's a lot of words. 1 km equals 1,000 meters. Okay? That is a useful mathematical expression. But if I'm going to try and solve a question, I want to be able to interpret that information and bring that into a form that I can actually use. Okay? So for instance, there happened to be precisely 482 kilometers from here to Disneyland. I want to know how many meters that is. Okay? Those of you like, oh, you just got to shift decimal. That's cool. That's cool. You can do that. It's going to screw you over later on. So don't do that. I want you to take advantage of the mathematical expression that we have here to be able to set up the work for this conversion. Okay? So this is an equality. 482 kilometers has to somehow equal some number times meters. Okay? Is kilometers the same thing as meters? No. So what does that mean has to happen? That kilometer unit must disappear from my system, which means I can place kilometers on the bottom. Where's my meter unit show up in my answer? On the top. Does it show up on the left-hand side of my equality? No. Not yet, so what can I do? Put it on the top. Okay? What is the relationship between meters and kilometers? 1,000 meters is 1 kilometer. Where does the 1,000 belong? No. For those of you at home, everybody just said 1,000 belongs on top. I am being a bit of a jerk on this. No, it does not belong on top. Where does the 1,000 belong? I don't accept numerator either. Getting closer. Where does the 1,000 belong? Nope, that's extra wrong. With the meters. Okay? And you might say, well, that's stupid, Mike. That's not a big deal. If we go through and accept 1,000 belongs on top, what happens the very next time you run a calculation? You put 1,000 on top. Why'd you put it there? Because 1,000 goes on top. No, it doesn't. It belongs with meters. If meters was on the bottom, the 1,000 is now being placed in the wrong space. Okay? The 1,000 is tied to meters. That means my 1,000 goes with meters. What number goes with kilometers?
1.
1. Notice, where did my power of 10? Okay, you know, well, there's no power of 10 there. Okay, 1,000 is the same thing as 1 times 10 to the third. So I could simplify this to being 10 to the third. What did I say kilo was? 10 to the third. Where does the power of 10 go? The power of 10 went with kilo?
No.
It went with meters. Our power of 10 will always go
The base.
with the core unit, okay, every single time. Okay. Where this becomes confusing is when we shift into the centi and milli, because we've come up with other ways to memorize those numbers or those conversion factors. Those other ways usually result in you screwing up this conversion and someone saying, well, which one's bigger, meters or kilometers? If I knew the answer to that, I wouldn't be asking you the question. Okay? That's always what goes through my mind every time somebody asks that. Okay? Which one's bigger? Yeah. Well, you're saying I'm wrong, so it must be the other way around. That's a 50-50 shot. If that's what you guys are doing to get through this, if I string two calculations together, your odds of getting the question right now, if each of them is 50-50, those of you who dealt with probabilities, you just dropped to a 25% chance of getting that question right with two 50-50 conversions. 50-50 isn't that bad, but two 50-50s is a 25%. If you get 50% on this exam, I'm going to be unhappy. If you get 25%, I'm quitting. I probably should if you got 25%. No one's ever gotten that. Don't test that. Okay? So what you need to do is think about why you're placing those numbers where they are. It's because the units tell you that. Okay? And in this system, or in this sequence of this unit, you're going to be doing conversions that you're like, this is a dumb conversion. Why are you making me do this? I'm not making you do a dumb conversion. I'm making you do an intelligent process. But at the same time, I'm giving you a dumb conversion so that when you get the answer, you're like, that number makes sense. Because now you trust the process. Once the process is trusted, when we move to a system where you don't have the comprehension of what those numbers mean, you can trust the process to get you to the right answer. So right now, this is self-confidence boosting. Get a process that consistently works. That's the whole goal in this unit, as far as calculations go. Kind of, sort of? Okay. So if you want to say, oh, I just shift the decimal, cool. I'm fine with it. Also do my process. Okay? Why go through all this work up here? What is 10 to the third meters over 1 kilometer equal? Like, what? What does that even mean? This is a mathematical expression up here, right? Okay. I want to match the one down here. Okay, meters is in the numerator, right? Kilometers on the other side, but I want it in the denominator. How do I get this 1 kilometer over to the other side? Divide both sides by 1 kilometer. This I thought was kind of mind-blowing when it happened. It's like stupidly simple, but it's like, really? Okay. What is 1 kilometer divided by 1 kilometer? It's 1. In this conversion, what did I just do? I multiplied by 1. Does that change meaning if we multiply by 1? No. But because the units are established there, it allows me to convert the units across. All of our conversions, we're multiplying by 1. We just have to pick the right one. Okay? That's like a meaning of all life, right? You just have to pick the right one.
42. Anybody?
Okay? So it's all a question of finding that. We're looking at our English. We've got our mathematics, which is an equality. If we play with that equality, we're ultimately solving it for 1. Okay? Do I need to have meters on top? No. I could have solved for 1 the other direction. It's still 1. It's just a question of how I decide to use it in the context of the question I'm setting up. Okay? There's a whole bunch of examples through that, so we're just going to kind of skip through that. Okay. This one is extra tricky. 10 to the positive 2 means what? Touché. I did not consider that. Yes, it is a big number. What does 10 to the 2 mean? What are you doing as a calculation? 10 times 10. That's it. It's just what 10 to the 2 means. What does 10 to the minus 2 mean? And because I've got it colored.
Times 1, 10. Times 1, 10.
Right? Bringing in fractions on me, that's confusing. Okay?
10.
Admittedly, I am going to bring in calculation or a fraction here. That minus sign, that negative, means run your calculation in the opposite location. Where is the 10 to the minus 2 currently located if this was a fraction? Where is 10 to the minus 2 located? Okay, so if I look at a fraction, right? I don't know why I'm writing fraction, but I am. We would have the top, and we'd have the bottom. Okay, or we'd have the numerator. I'm not writing all that out. Numerator over the denominator. Where's 10 to the minus 2 written?
Or the numerator.
It's in the numerator. This is over 1. Okay. What does that minus sign mean? It means run the calculation. What's the calculation? 10 to the second in the opposite location of where it is. Where is it currently located? In the numerator. So this is the same thing as running that calculation 10 to the second in the Notice what happened to the minus sign. It went away. Why? The minus sign is just saying do the calculation somewhere else. That's all it means. So once I get rid of that interpretation, I don't need to worry about it anymore. And I get my calculation. If you don't like this abbreviation, that's cool. Don't worry about it. But that abbreviation and that kind of simplification behind it is really useful in my opinion. Up to you which way you want to use it. So we'll skip through that. This ultimately is why we end up with our centimeter conversion. Okay, centimeters and meters. What did you guys memorize? For anybody that's memorized anything with centimeters and meters, what have you memorized? 10 to the negative 2. Are you saying that because I told you to memorize that? Yeah, then shh. You can't answer the question. Centimeters and meters. No one's memorized something else? I'll guarantee you all are liars.
Centimeters in a meter?
Okay. Sometimes we memorize 100 centimeters in 1 meter. The problem with that is you're now memorizing something that doesn't tie back to what the prefix means. Okay? Notice the power of 10 is located with meter, which is the core unit. Power of 10 with the meter, which is the core unit. It's a negative 2. What happens with negative signs? Our brains explode. We can't deal with it. So somebody was like, I don't like dealing with that minus sign, so I'm going to use that trick we just talked about. That trick was run the calculation in the opposite location. What is 10 squared? 100. Ooh, now I don't have to worry about that minus sign. The problem with this is where did the power of 10 just show up? Okay? With not the core unit. So if you go through and memorize that 100 centimeters is a meter as opposed to 10 to the minus 2 meters is 1 centimeter, you now have to be careful to place your power of 10 correctly because it's not consistent. Okay? All I want to say there, if you've memorized that, be careful with it. You have an extra step to memorize. If I tell you your prefixes to memorize, that's how you got to do it. We still got time. Admittedly, maybe this stuff isn't all that important. Converting, actually this one gets important. This is our big process. We already just worked through an example on this. Okay, let's see, do I actually have my, do I really not have my fun little example? Okay, 36 inches. I want you to convert that into feet. What do? Divide by 12, wrong. Multiply by 12, very wrong.
Multiply by 12 to the negative 3.
Okay, what happens if I divide 36 by 12? What do I get? 3 inches. Those are saying feet. In that calculation, do you see anything about feet? No. What did you do by dividing by 12? You're used to doing that conversion. You've internalized all of that. Stop it, for the love of God. Okay? And not because you're doing it wrong, but you've had a lot of experience with that. As soon as we shift into Unit 3, you won't have experience with those unit systems, and you will screw up every single conversion. Because you'll now be like, well, I'm going to divide by 12. Well, now I'm going to multiply by 12. Okay? You need a system to tell you why you do the calculation you do. Okay? So number 1, write down what you want as an answer. Equals. In this case, I said feet. What did we start with? Inches. Good answer. Not 36. We started with inches. 36 just happened to be the measurement tied to that inches. If I look left and right, across that, they aren't equal. The inches must disappear. What needs to show up? Feet. Do I have a conversion factor between inches and feet? Yes. What is that conversion factor? 12 inches. Pause. Where does the 12 tied to? Inches. Where does the 12 show up? Not in the denominator. With inches. Okay? 12 inches is 1 foot. Where does the 1 show up? With feet. Good job. Now what happens? Inches cancel. I would have my proper unit. Because I have my proper unit, now I can do the mathematics. Mathematics come second. Do all of the unit conversion first. Your textbook outlines this, and they call it unit analysis method, dimensional analysis. It's all the same thing. Step 1, what do you want for an answer? Units. What did you start with? Okay, units and the number. Your unit factor is now, how do I convert that? Okay, we'll pick up there. Sorry.